Hello, you guys. I prepared a video for PDF analysis from the scattering data, and the PDF stands for, is a pair distribution function. And in material science area, it is getting more and more popular with the development of the photon source, light source like a synchrotron source, and and neutron source as well, and even TEM. In the TEM, we are measuring like a diffraction pattern, and we calculate the PDF pair distribution function. So to make it short, I just describe as short as possible. The pair distribution function describes the distribution of the distance between the pairs of particles contained within given volume. You know, so this is quite the informative to really study in especially amorphous alloy or amorphous system, because in the crystalline alloy you would have some the imaging contrast between the lattices. So if you take the TEM, you probably see lattices, and you can easily really get the distance as a value, as a number from the image. But amorphous alloy, for example, they are sort of distributed. The atoms in the amorphous alloy distributed nearly random. There's a random distribution. So there is no enough contrast. Because of that, we need another tool. Not only the imaging, we need to directly measure the structural information of the material. This is sort of can be the PDF in PDF is can be it can be the possibility or option for that. So, but recently I learned that many students in material science area, they understand what is PDF. They know the concept of the PDF. But if I ask a little bit in deep, like the what is like a what is basis of the calculation of the PDF from scattered data, like a deflection pattern, then they have quite no idea. Many of them have no idea how to really calculate. And I take a look at some literature for that, but the math, there are quite certainly many the mathematical description for PDF calculation, but it is not straightforward to understand and digest directly what is really happening in during the scattering phenomenon. And actually, it is not easy to really visualize what is happening with the scattering, and what kind of thing is a basis we can make us to calculate the PDF. So those things today I want to a little bit demonstrate, and this is just animation I got from this web. And there is a single, for example, there is a single atom, and incoming like the plane wave make this atom scattered. The plane wave can be scattered by the atoms. So generally, like you throw a stone in the water, then there is also the water wave is outgoing from the scattering center. This is actually same in the photon point of view or electron point of view. Then you see probably here is their wave is getting larger and larger and propagate to the outer direction. But in case there is some pairs, another atom or more than two atoms there, then the scattered wave interfere each other. Some point there is a constructive interference, and some point the destructive interference. And if you take the detector there, probably you see the wave pattern, right? Because the probability of observation is actually depend on their how they interfere each other. So they're in such a position, if the waves are in constructive interference, then your probability of observation get higher. But at that point, it can be some certain angle or some time period. At that point, if the two waves destructive interfere each other, then the probability of observation get lower. So this is a basic thing. If there is more than two atoms, there is the wave pattern as a scattered signal. So in detail, let's imagine that there is only two atoms. This is incoming wave, and there is a bunches of atoms. And I, for convenience for demonstration, I just make like clusters there, and which consist of some several number of atoms. So imagine that just here red atoms and blue atoms scattered only. We neglect any other like a scattering happening in other in surrounding atoms. So what happened here is incoming plane wave come to the atom and scattered, as same as the animation before I showed you. Then you see probably here some fringes. Do you see what I'm seeing? Is there is a fringes as you show as I showed you in the previous animation as well. There is a fringes, and what you get in the detector. Let's imagine this the rectangular thing is a detector. Then you probably get like such a the wave. There is a, for example, there is a constructive interfering each other, and there is the destructive, and it is just some period. There is some frequency. Actually, this is depend on their distance. So let's imagine another happening. Like there is a, this is not the nearest neighbor. Let's say this is a second nearest neighbor. There is a two atom only scattered from the incoming plane wave. Then what happened here is everything is actually same. Just only the different. What difference is just the distance. The distance between the scatterers. And you see here also the fringes much get denser than before. I mean, now it's second nearest neighbor. If we compare to the first nearest neighbor, much dense. And if you observe in the detector, and you probably see such a like little bit denser wave to compare it with the previous one. And for the last example, just imagine one cluster. They're acting as a scattering point, and what happened here is you probably see their interference is much denser, and here is a wave. Their fringes is much more denser, much denser, yeah. And you probably see such a the very dense wave pattern there. So this is important. What we only change is the distance, the distance between the scatterers. But what we are getting is a frequency difference of the wave. So another word, the frequency in the observation actually depend on, they are representative of the atomic pairs, how much they are far away. I mean, how far they are. This is a very important point about this powder deflection technique. The frequency in the observation demonstrate or represent the distance, pair distance between the scatterers. So in detail, we can use a mathematic to describe such a waves. So again, probably in the observation in the real experiment, we get all bunches of information at once. Like we got the integrated information, not the decomposed information. So we can write a mathematical term that including this is just a pair distance, right? And there is a wave. So this is what we are seeing here. And this is just like we need to normalize, because this what I demonstrate to you before is just I neglect any kind of contribution of like you know atomic pairs. If your R value the atomic the center of the scatter the center of the scattering point, when the R value is larger, there is more probability to have the pairs. So in the reality, we need to compensate, and we need to normalize um, such a like the rising influence in the Q vector point of view. So this is just normalization, and the most important thing is we have the pair distance information here, and the wave sine wave there. But another thing we need to take account is actually there is a one scattering happening at the same as there's like the scattering happening from the structure point. If there is a one scatter there, like of one single atom, then the plane wave come here is it, and they scattered, and the probability of the observation of the signal is actually there is a exponential a decaying decaying function is there. This is we call just atomic scattering factor. Actually, this is just depend on the G, the atomic number, because if the one element or one atom in your specimen has a higher G, then there is more number of electrons in the orbit. Then there is it basically means there is more possibility to deflect photons or electron, neutron. Yeah, in neutron point, they directly react to the nuclei, and if the atomic number is higher, the nuclei also get the bigger. So those are just element, like I say, element constant. So here is boron, and here is iron, and so on. So we need to subtract those information from the observed signal. You know what I mean? These are the intrinsic background from the scattering events. So what we do is what we get is actually orthom image. This is just a scattering, the single atomic scattering factor, and there is structural information. If we write in mathematical version, then there is a scattering factor and there is a structure factor. So what we do is we can just subtract the single atomic scattering factor. It's easy, In most of case, we know our sample. I mean, we know the composition, elementary composition of our sample, and just we mathematically calculate what background it can be. Then we just directly subtract. This is a very easy step. And now we have a pure structural information. So we are call that as a structure factor. So you probably see here is the huge oscillation. Actually, those oscillation consist of incorporate like many kinds of sine wave scattered by first nearest neighbor, second nearest neighbor. If there is a cluster and cluster scatterings happening. So this structural factor consists of like whole whole structure information, scattering information from structure in one hand. So what we need to do is very simple. So this is an example. There is a different system, and you probably have a different structure factor because there, like for example, in the gases, there is no pair. They are just floating around the space. Then there is no pair, then you will have no structure factor. But in the liquid, there is in the liquid you probably have the random distribution of the atom because they are just moving around in the liquid state, and you probably have very just like a single wave like oscillation here. And in the glasses, amorphous alloys, or like a silicon oxide, then you probably see such a pattern. And the crystal, there is a huge peak, because in a certain distance, given distance, there is a, because it has a long range order. So in certain distance, there is a quite sharp peak because the atom is actually located in the certain R value and with the periodicity. Then to get the PDF, what we do is just a pre-transform. Let's go back to this one. This is actually what is sigma in the this sigma is actually in the linear algebra point we can write the sigma, but in the real mathematical, like a functional mathematical point, we just write as an integral. Then in the integral there is one function and 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 the wave function. There's two functions in the integral, and we want to extract the one. What is that? Just Fourier transform, right? So we just decompose the pair distribution from the structure factor with the Fourier transformation. Then we get the PDF. This is actually the way how we get the PDF. So finally, your PDF is a intensity or whatever the signal as a function of the R value. R is just radius on the, like in given atoms or given particles in your specimen. Then you probably see the first nearest neighbor. We call first coordination share. This is a blue line, and there is a sharp peak, and you will have a second the coordination share, and third, so on. Very interestingly, if you believe the background subtraction, and if your calculation is fairly well, then you can also calculate the coordination number. How many atoms surrounding in the given the center atoms. This really gives you quite important information to understand your structure of your specimen, because the local density is very important to the macroscopic material properties. So I hope this is actually all I prepared for today, and I hope it's really helpful for you, and see you next time. Thank you.